So imagine for a second that you're just, sitting at your desk, maybe drinking your morning coffee, and you reach down to plug in your desktop computer. But instead of routing that cable to a standard wall outlet, the line basically runs out the door down the hall and plugs directly into a live, fully operational nuclear reactor.
I mean, that sounds like an incredibly over-the-top way to make sure your video games never lag.
Yeah.
Or, like a scene from some sci-fi movie set on Mars.
Right, but that isn't fiction. I mean, it literally just happened on a live stage. So today we're doing a deep dive into this massive physics milestone that the American nuclear industry just quietly pulled off in like the span of 4 weeks.
Yeah, between June and July of 2026. It's wild.
Exactly. And we're going to figure out how these four radically different nuclear microreactors achieve this and why this pocket-sized nuclear revolution might actually be the only thing capable of saving the whole artificial intelligence boom from this devastating energy and water crisis.
Which is a very real crisis right now.
Oh, absolutely. So our sources today, they really run the gamut. We're pulling from industry mainstays like nuclear news, tech reporting from Tom's Hardware, some deep tech research notes from Hyperframe, and then obviously the official releases from the Department of Energy and the NRC.
It really is just this fascinating intersection, right?
Mm.
Because you have a sector that is historically defined by, red tape and these decades-long construction timelines, and suddenly it's operating with the speed of a Silicon Valley software startup.
Yeah, hitting milestones that usually take 10 years in just a few months. Like, for instance, hitting criticality.
Right, which is that ultimate physics threshold where a nuclear chain reaction sustains itself, without human intervention.
Yeah.
That is usually a grueling slog.
But one of these startups, All Atomics, they went from literally breaking ground to a sustained chain reaction in 8 months. So the obvious question is, why now? Like, how did the industry suddenly just break the speed limit?
Well, it was driven by a really specific government deadline paired with, honestly, a pretty brilliant regulatory workaround.
Okay, tell me about that.
So specifically, we are looking at Executive Order 13301. Now, this was a directive from the Trump administration. And just to be very clear for everyone listening, we're looking purely at the mechanics of the policy here and how it structurally altered the timeline. We're not taking any political stance, just focusing on the factual rollout.
Right, exactly. Just looking at the actual text of the order and what it did.
Exactly. So that order set this massive stretch goal. It said we need at least 3 advanced test reactors to achieve criticality by the nation's 250th birthday, which was July 4th, 2026.
Which is, I mean, setting a deadline is one thing, right? But making it legally possible is a whole other beast. Because
Yeah.
usually, if you want to build a commercial nuclear reactor, you have to go through the Nuclear Regulatory Commission, the NRC.
Oh, yeah. Years of reviews.
Right, like endless environmental reviews, safety analyses, having to prove that every single, valve and pipe is absolutely flawless before you even pour a single yard of concrete. So how did they get around the NRC for this?
Well, they essentially used the Department of Energy, the DOE, as the authorization body instead of the NRC.
Yeah.
So the DOE created these two things, the Reactor Pilot Program and the Nuclear Energy Launchpad.
Okay.
And this allowed private developers to actually build and test their experimental reactors at national labs. So places like the Idaho National Laboratory, they could test them under the DOE's own jurisdiction.
Oh, I see. So it's kind of like it's like getting a special permit to test drive an experimental hypercar, but you do it on a closed government track.
Yes, perfect analogy.
Right. So you get to prove the aerodynamics and the engine physics actually work in the real world instead of waiting, 5 years to get the car street legal for public highways with the regular transportation department.
Yeah, and to push that hypercar analogy even further, the DOE essentially owns the racetrack, and they employ the safety crew. So they aren't just handing out permits and looking away. They're actively overseeing the documented safety analyses right in their own highly controlled backyard,
Right.
which cuts out years of bureaucratic back and forth because the DOE already has the internal expertise to validate these first-of-a-kind designs quickly and safely.
But I do have to wonder, I mean, is this just a one-time stunt? Like, just to hit a July 4th political deadline, does this DOE pathway actually change how nuclear technology gets deployed commercially in the real world?
That is the multi-billion-dollar question.
Right, because if you still have to go through a 5-year NRC process to put one of these in a commercial data center later, an 8-month lab test doesn't really solve the long-term problem,
Exactly. But the Hyperframe research notes we reviewed highlight that this actually isn't just a temporary loophole. Some of these developers are actively challenging the NRC's asserted jurisdiction over DOE-authorized test reactors.
Oh, wow.
Yeah, so if that legal maneuver holds up, this DOE authorization process could genuinely become a viable, permanent route to commercial deployment. I mean, it would fundamentally rewrite the timeline for nuclear innovation in this country.
That's huge. And the innovation itself is what really stands out in these blueprints to me. Because the government didn't just order, 4 identical reactors. Between June 4th and July 4th, we saw 4 entirely different mechanisms hit criticality.
4 totally different flavors of fission,
Yeah. So first up, you had Antares Nuclear on June 4th with the Mark Zero, which is a sodium heat pipe reactor.
which, by the way, is just a brilliant piece of engineering. A heat pipe reactor essentially operates with no moving parts in the core cooling system.
Oh, really?
Yeah, think of the passive heat pipes used to cool a really high-end gaming laptop, but scaled up to nuclear temperatures. It uses the phase change of sodium, so it vaporizes and condenses to move heat away from the core completely passively. It's incredibly robust.
That's amazing. Okay, and then 2 weeks later, you have Velar Atomics hitting criticality with the Ward 250, and this one is cooled by helium and uses a highly specific fuel called TRISO. And what caught my eye here is actually the location. Valar built this at the Utah San Rafael Energy Lab, so that makes it the very first DOE-authorized reactor built and run outside of a traditional national lab.
Yeah, that was a huge deal. And the mechanics of Velar's design are so crucial for understanding their commercial strategy. By using helium as a coolant instead of water, they solve a massive environmental issue.
Because it's an inert gas, right?
Yeah, exactly. Helium doesn't become radioactive, and it can operate at these incredibly high temperatures without turning into a, corrosive, highly pressurized threat the way steam does in a traditional water-cooled plant.
And that ties directly into the TRISO fuel they use. Because TRISO is, it's basically the jawbreaker of the nuclear world.
That's a good way to put it.
Right. Instead of packing uranium into those long metal rods that can melt down if they get too hot, they encapsulate these tiny uranium kernels inside multiple microscopic layers of carbon and ceramic.
Right.
And that physically traps the radioactive byproducts inside the fuel pebble itself.
Which is exactly why these advanced microreactors don't require those massive dome-shaped concrete containment buildings that, totally define 20th century nuclear plants.
Okay.
The containment is literally built into the fuel itself.
Wow.
It cannot physically melt down, even if you lose all active cooling.
Okay, so then you have deployable energy coming online June 30th with the Unity reactor. This one is a water-moderated, gas-cooled 1 megawatt system. And finally, hitting the July 4th deadline right on the nose, Allo Atomics brought the Allo X online, and they use liquid sodium as a coolant.
Yep, so they beat the government's goal of 3 reactors by delivering 4.
Which is great, but I do have to push back on this strategy a little bit. Like, if the goal is to build out commercial power rapidly, isn't this quote-unquote portfolio approach a complete manufacturing nightmare?
How do you...
Well, you can't build a massive automated assembly line if you are constantly retooling your factory to switch between helium cooling and then sodium heat pipes and then liquid metal. Shouldn't we just, I don't know, pick the absolute best design and standardize it like we do with Boeing or Airbus?
I mean, it definitely sounds inefficient until you look at the harsh reality of global supply chains.
Yeah.
The government and these companies are deliberately hedging their bets here to avoid industry-wide bottlenecks.
Okay.
For example, to get that incredible performance out of the Antares and Velar reactors, they require a highly specialized fuel called HLEU, high-assay low-enriched uranium.
Right.
And right now, the domestic supply chain for HLEU is, well, it's still maturing. If there's a sudden shortage, a company relying purely on that fuel just grinds to a halt.
Ah, which totally explains deployable energy strategy then. Because the blueprints for their Unity reactor show it was explicitly designed to use standard 8% low-enriched uranium, or LEU.
Yeah.
So they deliberately engineered a less exotic reactor so they could tap into the existing robust commercial fuel supply chain that already powers the legacy plants today.
Yes, and furthermore, they aren't all competing for the exact same customer anyway. Valar's high-temperature gas reactor is perfect for industrial manufacturing that needs, extreme heat for chemical processes.
Right.
Whereas Deployable's 1 megawatt unit is designed for supreme mobility. So by funding all four, the DOE is ensuring that even if one technology hits a regulatory or a supply chain wall, the broader microreactor ecosystem survives and can still scale.
And scaling fast is critical because avoiding bottlenecks is exactly why this entire industry is pivoting toward a brand new customer base.
Hmm.
I mean, you can manufacture all the localized microreactors you want, but if the traditional grid infrastructure can't handle the transmission load, it doesn't matter.
Very true.
Which brings us to an industry that is currently choking on its own massive growth, and that is artificial intelligence.
Yeah, the hyperscalers, the companies that are training and running the next generation of large language models, they are facing a brick wall of physics and public opinion right now
For sure.
because all that demand for compute power translates directly into a need for raw electricity and massive, massive amounts of water for cooling.
And the stats from Tom's Hardware, they really put this into stark perspective. In just the first 4 months of 2026, over 75 data center buildouts were successfully blocked by local communities across the U.S.
Wow, 75.
Yeah, and honestly, you can't really blame the locals. In one major region, the influx of AI data centers triggered a 76% electricity price spike for residents.
That's insane.
Plus, these facilities are just incredibly thirsty. AI operations are projected to consume up to 600 billion gallons of water by 2030, and that's mostly for evaporative cooling in the server farms.
Right, and you simply cannot scale an industry if every single time you propose a new facility, the surrounding town revolts because their water table is dropping and their utility bills are doubling. It is literally an existential crisis for the tech sector.
Exactly.
Which is why that live demonstration by Valar Atomics wasn't just a cool parlor trick. It was a proof of concept for survival.
Okay, so let's break down the mechanics of that live demo we mentioned at the start of the deep dive. So Valar took their Ward 250 reactor and ran it at about 37% of its test output, which generated roughly 100 kilowatts of thermal energy.
Right.
They extracted that intense heat using their pressurized helium system, ran it through a thermal electric generator to convert the heat into an electrical current, and then literally ran a cable right to the stage to power an NVIDIA RTX Spark desktop PC.
Yeah, and that PC was hosting a live web page appropriately named nuclearwebsite.com. It was wild. The CEO, Isaiah Taylor, stood on stage and explained that 10 to the 15th power uranium atoms were fissioning every single second just to maintain that current.
It's a really tangible demonstration of absolute independent power.
And they aren't stopping at a single desktop, obviously. Valar and NVIDIA just announced they are exploring the construction of a 30-megawatt closed-loop AI factory in Utah.
And the operative word there is closed loop. Because it uses that high-temperature helium cycle, it doesn't rely on those massive evaporation towers. It completely removes the local water consumption issue that is driving so much of the public backlash.
This represents a tectonic shift in how we think about civic infrastructure. Instead of a tech giant building a massive data center and then begging the local utility grid to, route a gigawatt of power to them.
Right, often waiting years for transmission lines to be built.
Exactly. Now they are shifting to a behind-the-meter model. They intend to generate their own baseload power on-site, entirely independent of the public grid.
It completely flips the script on how nuclear power is built, too. Historically, a nuclear plant is a custom-built mansion. It is a massive, bespoke construction project that takes a decade of pouring concrete and welding pipes on site.
Right.
But these microreactors change the model to a factory assembly line. ALO Atomics is currently planning a 1 million square foot factory to pump out 100 reactors a year. They essentially want to turn nuclear reactors into Lego bricks.
That's a great way to visualize it.
Yeah, their base unit is 10 megawatts. So you just order, say, 5 of those factory-made identical bricks and snap them together to create a 50-megawatt ALO pod right in the parking lot of your data center.
It's modular.
But wait, let me play devil's advocate here for a second. Hyperscalers like Microsoft, Amazon, Google, they are used to buying power by the gigawatt. Trying to satisfy the ravenous appetite of a billion-dollar AI training cluster by stringing together these tiny 10-megawatt microreactors sounds kind of like trying to power a naval battleship with, thousands of AA batteries.
I mean, I hear you.
Does the math actually pencil out at that scale?
It does, but it requires a shift from managing a single massive turbine to managing a decentralized fleet. So yes, a single 10-megawatt reactor is indeed a drop in the bucket. But if you have a factory churning out identical units, you achieve economies of scale in manufacturing rather than in physical size. ALO is actually actively collaborating with NVIDIA and Microsoft on automated reactor fleet management software. The concept is to manage dozens of these small, standardized reactors using the exact same operational logic a data center uses to manage racks of servers.
Oh, I see. So if one server rack goes down, the data center doesn't go dark. If one 10-megawatt reactor needs routine maintenance, the other 40 in the cluster just seamlessly take over the load.
Precisely. It builds extreme redundancy into the physical power layer. And most importantly, it guarantees uninterrupted operation, insulating these tech giants from rolling blackouts or regional grid failures.
Which brings us to the other massive sector driving this market, and it's one that values redundancy and absolute power independence above almost everything else, the military and the space program.
Yeah, the Department of Defense views their reliance on the civilian grid as a critical strategic vulnerability. If you have a drone command center or an early warning radar installation, you absolutely cannot afford to lose power because of, a severe weather event or a targeted cyber attack on a local civilian utility.
And relying on backup diesel generators is just a logistical nightmare. That's exactly where a company like Antares Nuclear is stepping in. They just closed a $96 million Series B funding round, and they are squarely targeting the DoD's Janus program.
Right.
The Janus mandate requires operational nuclear microreactors on U.S. military bases by September 30, 2028. And we already know the Air Force has selected Buckley Space Force Base in Colorado and Malmstrom Air Force Base in Montana as the first potential sites.
The tactical mechanics of this are just profound. Currently, maintaining power at remote or contested military bases requires a constant, unending supply line of diesel-fueled trucks.
Yeah, which are targets.
Exactly. Those convoys are incredibly vulnerable targets in a conflict zone. A microreactor completely changes the paradigm. You fly a containerized reactor in on a C-17 transport plane, set it up, and you immediately have reliable zero-carbon baseload power for 5 to 10 years without ever needing a single fuel delivery. It completely severs that logistical tether.
And that tether gets even harder to maintain when you leave the atmosphere.
For sure.
Antares is also aiming for NASA's Fission Surface Power program. The objective there is to establish a 100-kilowatt reactor on the lunar surface by 2030, because you obviously can't run a diesel generator on the moon, and solar panels are wildly inefficient during the 2-week-long lunar night.
And this same philosophy of resilience and independence, it applies just as much to civilian infrastructure. Deployable energy, with their 1-megawatt Unity reactor, actively refers to their technology as a highly transportable nuclear battery.
A nuclear battery.
Yeah, they are engineering these systems for remote Arctic communities, critical industrial sites, and disaster response scenarios.
Meaning if, like, a Category 5 hurricane wipes out the transmission lines in a coastal city, FEMA doesn't just have to bring in pallets of bottled water and temporary diesel generators. They can literally truck in a deployable energy nuclear battery, drop it in the parking lot of the regional hospital, and plug the critical care units directly into a continuous megawatt of power.
Exactly. It is about creating islands of stability that do not require a functioning centralized grid to operate.
I mean, I understand the vision, but I do have to challenge this timeline a bit. We are sitting here today looking at data from zero-power criticality tests. Proving the physics work in a highly monitored government lab in Idaho is a massive achievement, yes. But the military wants these powering actual strategic bases in just 2 years, by 2028, and NASA wants them on the moon by 2030? Aren't we vastly underestimating the leap from a carefully controlled science experiment to a commercial product deployed out in the wild?
Oh, it is an incredibly steep curve, and skepticism is absolutely warranted here. As the analysis in Human Progress pointed out, reaching criticality and running a reactor that steadily produces commercial electricity 24/7, those are two totally different engineering disciplines.
Right.
So far, none of these 4 reactors have operated at commercial power for any meaningful duration. The next 12 to 24 months are really the crucible for this entire industry.
So the physics are proven, but the commercial endurance is still a massive question mark.
Exactly. Which is why all eyes are on ALO's Project Ascension.
Yeah.
They are already moving to build a second commercial-scale 10-megawatt reactor at their Idaho site with the explicit goal of powering an on-site data center by 2027.
Wow.
Yeah, that is the real test. Can they move from bespoke lab testing to reliable manufacturing, string them together in a fleet, and keep them running without a single thermal hitch?
That is definitely going to be the defining moment. So let's distill all of this for you, the listener, because we have covered a massive amount of ground today. What does this deep dive ultimately reveal?
The overarching takeaway is that the nuclear industry has fundamentally changed its measuring stick. We have transitioned from measuring progress in decades and billions of dollars to weeks in agile manufacturing milestones. We're watching deep tech nuclear startups scale with the speed, capital, and aggressive iteration that is usually reserved for Silicon Valley software companies.
And before we wrap up, we want to explicitly remind you that while we spent time discussing political catalysts today, like the Trump administration's Executive Order 14301 and the regulatory pathways opened up by the DOE, we explored those purely to explain the policy mechanics that allowed this incredibly rapid innovation to happen.
Right.
We are not taking sides or endorsing any political viewpoints. We are just decoding the factual blueprints of how a decades-long timeline was compressed into a single month.
And the physical results of that compression are undeniable. Between the diverse portfolio of cooling technologies, the ability to fast-track safety testing at national labs, and the honestly desperate blank check commercial demand coming from the AI sector, the era of the nuclear microreactor is officially here.
And whether you are deep in the tech sector or not, this race is going to directly impact the infrastructure of your everyday life. The success or failure of these microreactors will dictate the cost of your monthly utility bill, the security of the water supply in your local town, and even the processing speed of the AI applications you interact with daily.
We are watching the real-time decentralization of heavy infrastructure.
Which leaves us with a final, mind-expanding question for you to ponder long after this deep dive ends.
Okay.
We started our conversation by imagining plugging your personal desktop computer directly into a localized nuclear reactor.
Yeah.
If companies like Allo and Valar succeed in making factory-built, snap-together nuclear batteries a commercial reality, what happens to the traditional centralized power grid? If every neighborhood, every manufacturing plant, and every massive data center can simply buy their own independent nuclear power source and site it right in their backyard, do we even need a national grid anymore? Or does the very concept of a shared electric grid relying on hundreds of miles of fragile transmission lines just become a relic of the past?
It is definitely something to think about the next time you flip a light switch.
Thanks for joining us on this deep dive. We'll catch you next time.